first part of class. So if you don't have your notes out, you can get your notes out. Looks like this, right? Chapter 8. If you didn't pick up the notes last week, there are some on the side counter if you want to pick those up. But what I'm going to do is we're going to go through the questions on video 1.7 and then practice on that. And then questions over 1.8 and practice with that. If we don't get to everything today, we'll have some time to continue looking at it tomorrow if needed. And so what I did is first I went through the questions that you guys had on each of the videos to kind of just make these general review slides. All of this was in the notes, and we're going to spend a lot of time on the graph itself. So if you're like, well, I asked a question on the covalent bonding graph, but I don't see it here, that's because we're gonna be talking about that all on its own. So for video 1.7, this is on types of bonds. And we're going to look at ionic bonds, covalent bonds separately. Metallic we talk a lot more about like November. We'll talk about metallic bonding. So when atoms come together to bond, they're achieving the lowest energy, and we'll look at what that looks like on the graph. But essentially what that means is any attraction is balanced out by any repulsion. So we don't have to worry about the atoms getting too close together. They're in the perfect stable arrangement. With ionic bonds, they have very high melting points because they have a really strong attraction. And we're going to be talking about lattice energy as well. There's some questions on lattice energy, so I'll make sure that goes back to Coulomb's law. I told you we're going to be going back to Coulomb's law a lot this year. Lattice energy is another one. Covalent bonding, we're going to be looking at a lot throughout this week because Lewis structures are based on covalent bonding for the most part. The graph is based on covalent bonding, electronegativity differences. We're looking at polar and nonpolar covalent bonds. And then bond order. So there was a couple questions on bond order. And I just copied and pasted this table from your notes. So this table is on page 3 of your notes, where it talked about bond order, length, and strength. So bond order is really just how many bonds are between atoms. If there's one bond order is 1. So if it's a single bond, the bond order is 1. If there are 2 bonds, if it's a double bond order is 2. If it's a triple bond, that's 3 bonds, bond order is 3. And then in this table, it also shows based on the strength and the length. So single bonds are the weakest bonds that exist, and they're the longest, because there's not as much attraction between the nuclei of the 2 atoms. Triple bond is the strongest, and so since it's the strongest, there's the most attraction. That's the shortest bond. And that is going to be useful when we look at the covalent bonding graph as well. So bond order is just the number of bonds that are between a pair of atoms. And again, this table is right out of the notes on page 3. So the first thing that we'll look at from video 1.7 is going to be lattice energy. So lattice energy was at the bottom of page 1 of the notes. And lattice energy is looking at the strength of ionic bonds. So we're looking at the strength of ionic bonds. And for ionic bonds, typically it's a metal and a nonmetal. The true definition of an ionic bond is it's the attraction between a cation and an anion. So you could technically have an ionic bond without a metal, because NH4 plus is a cation that doesn't have a metal in it. And so as long as you have an attraction between a cation and an anion, you're looking at an ionic bond. Now the definition of lattice energy is the energy required to completely separate 1 mole of a solid ionic compound. Okay, essentially, if I paraphrase this, lattice energy is the energy required to separate an ionic compound, to break an ionic bond. breaking bonds, and we talk about breaking bonds more in the next unit, I believe. Breaking bonds always requires energy. It's always endothermic. If I think about a bond like a stick, and I want to break the stick, I have to put energy into it. It takes energy for me to break the stick, just like it takes energy to break any bond, ionic or covalent. When we look at bond strength, we actually focus on the opposite, which is why if you see exothermic values, you see negative values. It's because if you form a bond, it's always exothermic. Again, we talk about this more later, but there were some questions on how do we know if it's exo or endothermic. Now, the strength of the bond. The strength of any ionic bond depends on the charges of the ions and the distance between them, because it's based on Coulomb's law. Coulomb's law is Q1, Q2 over distance. So the higher the charges, the stronger the bond, and the closer the ions are together, the stronger the bond. And so that was at the very bottom of page 1. It says the lattice energy increases as the charges increase and as their radii decrease. So the higher the charges and the closer together they are, the stronger the lattice energy. So if we look at some examples, so instead of having you actually do the video 1.7 examples on your own, we're actually going to be going through them together. Sorry, we're going to kind of be flipping back and forth, but I figured this will be kind of the best way to go through, especially lattice energy. And a lot of this practice, like today in the notes, is because they've started, and by they I mean College Board, has started asking more and more questions on both lattice energy and that covalent bonding graph. Last year on the free response, every single free response question had something related to lattice energy and something related to that graph. So if we look at number 1, right, and again, this is on page 4 of the notes. So this is actually part of the bonding practice. It says, why does MgO have a higher lattice energy than NaF? So we're focusing on MgO versus NaF. Lattice energy immediately tells us that we're relating it to Coulomb's law. So again, Q1, Q2 over d squared, that's Coulomb's law. Force of attraction is going to be based on Coulomb's law here. Here's what I do when I see lattice energy. The first thing that I think of is, okay, look at the charges first. So what's the charge that Mg will carry in an ionic compound? +2. And then oxygen is -2. Look at the same thing for NaF. +1, -1. So we want to look at charges because the higher the charges, the stronger the attraction. So this is going to help us actually answer the question. Okay, so here's what I'll start by saying. Although the ionic radii of Mg2 plus and Na plus are similar, and I know that they're similar because if I actually look at the periodic table, Na plus will have the same configuration as neon, Mg2 plus will have the same configuration as neon. The valence electrons occupy the same energy level. Magnesium will be slightly smaller, but not that much smaller. So although the ionic radii are similar, the magnitude of the charges, magnitude just means the value. So when you see the term magnitude, that just means the value of whatever. So magnitude of charges means +2 versus +1, or -2 versus -1. So the magnitude of the charges on the ions in MgO are greater than NaF. I'm being a lot more, what's the right word, wordy in these responses, just so that when you go back and you're looking at these to review, you're like, oh yeah, okay. If you said the charges in MgO are greater than the charges in NaF, that's fine, because that's correct. So if we look at number 2, explain why NaF has a higher lattice energy than KCl. Okay, so the first thing you want to do is look at charges. What are the charges on NaF? +1 and -1. What about KCl? So they have the same charges. So charges can't be the reasoning here. You have one of 2 reasons for lattice energy, charges and distance. So that means that if NaF has a higher lattice energy, we should look and verify, but that means that Na plus and F minus are closer together than K plus and Cl minus. And that's the case. Right? Na plus and F minus are smaller ions than K plus and Cl minus. So the magnitudes of the charges in NaF and KCl are the same. So the difference is that the ionic radius of Na plus is smaller than K plus. Right, and I'll put in parentheses the ionic radius of F minus is less than Cl minus. So Na plus is smaller than K plus, and F minus is smaller than Cl minus. So the distance between the ions is less. Na plus and Cl, F minus. And KCl. Alright, so the distance between Na plus and F minus is less than K plus and Cl minus. So the higher the charges, the closer together the ions, the stronger the lattice energy. So based on kind of what we did in 1 and 2, we'll talk about the justification together, but see if you can put these 3, so LiCl, KBr, and MgCl2, just see if you can put them in order. So in order of increasing lattice energy means least to most, so weakest to strongest. We'll do the justification together, but see if you can put them from weakest to strongest. So the weakest attraction will be the smallest charges and the farther apart. Stronger attraction will be the higher charges and closer together. So I always start by labeling the charges. So LiCl, KBr, both are +1, -1. MgCl2 is +2 and -1. So if you look at charges first, I notice that Mg carries a +2 charge. So that is going to be the greatest lattice energy. Then I'll look down here for the least. So the least lattice energy, the weakest energy will be the smallest charges and the farther apart. So I'm looking at LiCl and KBr right now. If I look at the periodic table, right, just thinking about trends, K plus will have the same configuration as argon. Li plus will have the same configuration as helium. Argon's valence electrons are in N equals 3. That's a lot further from the nucleus than N equals 1. So LiCl, these ions will be close together. I should say closer together compared to KBr. So KBr will actually be the weakest, then LiCl, then MgCl2. And it says to justify your answer, so we kind of just did, but I'll go through again. So we can say MgCl is greatest due to the charge on Mg. And magnesium carries a 2+ charge. The other ones are all +1. And then we'll say LiCl is greater than KBr because the ions are smaller. So the smaller the ions, the closer together they are, and the stronger the attraction. So this is really just thinking about magnets. The stronger the magnet is like the stronger the charge. So it's going to be really attracted and close together. And then think about just two of the same magnets, right? Two sets of the same magnets. The closer together they are, the stronger that attraction. Farther apart, not as much attraction. Okay, so this is thinking about lattice energy. So then number 4. So read through number 4 and see if you can at least kind of like reason through in your head why the information that they give you is true. So read through number 4 and just see if you can kind of reason through in your head. We'll write the explanation up on the board. But based on what we did in 1, 2, and 3, see if you can kind of think through the answer to number 4. This was part of a free response question as well. All right, so it tells you in the question, the energy required to separate the ions is known as lattice energy. As shown in the table, the lattice energy of strontium hydroxide is less than the lattice energy of magnesium hydroxide. Explain why in terms of periodic properties in Coulomb's law. So periodic properties means the location on the periodic table. Coulomb's law means you're looking at charges and distance. So if I start by looking at the charges, all right, notice here both Mg2+ and Sr2+ have the same charge. So charges can't be our reasoning here. So then we're looking at the size. So let's look at the size of Mg2+ versus Sr2+. Mg2+ carries the same configuration as neon. Sr2+ carries the same configuration as krypton. So we can say the Sr2+ ion is larger than Mg2+. Because it has more occupied energy levels. There's periodic properties. Talking about information on the periodic table. So then, Coulomb's law says that the force of attraction is inversely proportional to the distance between the charges. Here's what we'll say. Since the distance between Sr2+ and OH- is greater, the attractive forces are weaker. So again, since the distance between Sr2+ and OH- is greater, the attractive forces are weaker. So the lattice energy is smaller. So when it comes to lattice energy, we're looking at charges and distance. So we're still looking at periodic trends. knowing kind of the way the trend works. We're still looking at location on the periodic table. But when you see something related to lattice energy, that means you're looking at either charges or distance. Any questions on lattice energy? So lattice energy is all about ionic compounds. It's the energy required to break an ionic bond. If there aren't any questions, so we're going to shift to covalent bonds now. So this is on page 2 of your notes. So I didn't actually talk about this in the video because we're going to talk about it in class. This is something that is relatively new within AP. I spent one slide on this last year because it wasn't much, and then they asked almost an entire free response question on this. So we're going to talk a little bit more about this. So this is a potential energy curve for covalent bond formation. So this is looking at forming a covalent bond. The difference is that ionic bonds, electrons are transferred completely. Covalent bonds, the electrons are shared. So that's kind of where we look at the main difference. So this potential energy curve, we're going to look at the formation of hydrogen. So on this, and you have a completed curve, I'm going to kind of show step by step. So when we have just two hydrogen atoms, we have them pretty far apart. There's no attraction or repulsion between them, so the potential energy is 0. Potential energy is the energy stored in bonds. So potential energy is going to be the energy stored in bonds. If we look at the x-axis, so the x-axis is labeled internuclear distance. Internuclear distance, so that means it's the distance between the nuclei. Right? Distance between the nuclei as we look at internuclear. And I think, yeah, I've labeled some of this stuff kind of right underneath the graph for you. So the distance between the atoms essentially shows the bond length. Right? The internuclear distance would show the bond length. When we look at a graph as well, I have this labeled, but if potential energy is greater than 0, that's an unstable arrangement between the atoms. If it's below 0, so your y-axis is potential energy. If anywhere on this graph is below 0, that's a stable arrangement. This is 0, so this is kind of really nothing. So initially, the atoms were far apart. Then we start to bring them closer together. So as we start to bring them closer together, there's some attraction between the atoms. Right? Not much repulsion because they're not very close together. You're not going to see a lot of repulsion until the atoms get really close together. Because then you have the nuclei of both repelling because they're both positive, and you have the electrons of both repelling because they're both negative. So as you start to bring them closer together, you have some attraction, and so potential energy is decreasing. That means it's becoming a more stable arrangement. Because as potential energy decreases, it's becoming more and more stable. So then we look right down in the valley. So right down here in the valley, that is where we have hit the lowest potential energy possible. This is where there's balance between the attractions and the repulsions of the atoms. So we're at a perfect balance of attraction between the nucleus of one atom and the valence electrons of the other, or the other way with the other atom. When potential energy is the lowest, that's where we're going to form the bond. Because that's the most stable arrangement. Because we've hit the lowest possible potential energy. So when we get down to this valley, this is actually where we can look at the bond length and where we can look at the bond energy. Now we're going to talk about bond energy much more when we talk about formation, exoendothermic, right? So when we do thermochem, bond energy is always the energy required to break a bond. Now this is showing the formation, which is why it's negative. So showing the formation, which is always exothermic. If If we wanted to break the bond, it's just the opposite number. So instead of negative 400, it'd be positive 400. And so right here, this is probably one of the most important things of these covalent bond graphs, is that when we're down here in the valley, this is where we look at bond length. It's the distance between the atoms. And so for this, right, we could figure out the bond length by looking at the internuclear distance. We'll notice a different bond length for every bond. Right? The H2 bond will be different from the Cl2 bond, or the O2 bond, or the N2 bond. It's all based on, is it a single, double, or triple bond, right? And what are the atoms? Now, if we continue to bring them closer and closer and closer together, as you bring them closer and closer together, you're going to get more and more repulsion. So that's going to cause the potential energy to increase. This is an extremely unstable arrangement, because now everything is wanting to repel, push apart. So the best place on this covalent bond graph is down here in the valley, because that's where the perfect bond is forming, and that's where we'll be able to look at bond length and bond energy. So we're going to take a look at the two examples, and I pulled these examples from practice AP questions. So we're flipping back to page 4. We're going to do the last two questions on this practice, and then you have like this whole practice page done. So number 5 says 2 molecules. They're both XY, but one is a single bond and one is a double bond, are drawn on the potential energy diagram to the right. Based on the two curves, which curve represents the single bond and which represents the double bond, and how do you know? So if you notice here, we have the two curves. Right? And I know you don't see the colors in your notes, but one is a solid line and one is a dashed line. What we look at when we look at these curves, really for us, is the energy and the bond length. So if I take a look at both of these, and you have these two lines that represent each. So the first line actually matches the red, the second line matches the dashed curve. Single bonds and double bonds are different lengths. And that's what that table was that I went through in that review slide. So if I look here, this dashed line is a little longer. All right, the solid line is a little bit shorter. Just based on that, we could actually identify them. All right, longer versus shorter bond. The longest possible bond that we can have is a single bond. It goes single is the longest, then double, then triple. Right, getting shorter and shorter. So here's what I'm going to say up here. So I'll put dashed curve and solid curve. Because for you guys, red and blue aren't really going to make sense because you don't see the colors on here. So the dashed curve is the one that's longer. The dashed curve is the single bond. So then it says, how do you know? Well, here's what I'm going to say. It's the longer bond length. Single bond is longest. And then the other reason is if we look at the energy here. The dashed line is also less energy. It's a lower bond energy. So we'll say smaller bond energy. Single bonds have low bond energies and they're very long because they're easy to break. Then we can say the opposite for the solid curve. So the solid curve is the double bond. First, it's shorter in length and higher in energy. Now, I know when you look at this, you're like, well, but this is technically a lower number. Right, here we're at like negative 300. Here we're at negative 600. The more exothermic, the more energy it would take to break. The more energy that's released when you form it. So that's actually where these curves tell us bond length, bond energy. Single bonds are always the longest bonds. Triple bonds are always the shortest. Triple are also stronger in energy because they are so close together.
This might be a stupid question, but how did you know it's longer? Because the
I was
blue
thinking
line.
the same.
Yeah,
It's
because the
farther right.
because the x-axis is distance, and so since the blue line here is farther to the right, that means that it is. So it's like this is like negative, or this is 150. This is like 140.
Okay, that's what
Yeah.
I thought.
Yes. Yeah.
That was actually a good question.
Really?
Because I was thinking the same.
Yeah. So if we look at number 6, this looks at another curve, but this is one of those, the student makes a prediction, are they right or not? So number 6, potential energy curve is given for C triple bond O. Okay, so I'm just going to kind of circle this. I'm just going to remind myself, triple bond is shortest bond. I just want to remind myself that triple bond is the shortest, just in case we need that. So it says a student claims that the curve for a C single bond O would be less deep and shifted to the right. Do you agree? Why or why not? So I'm just going to draw what the student says. So less deep and shifted to the right. So that means my peak is going to be to the right. Less deep means it's not going to go down as far. So maybe something like this. And we'll keep it go up to 0 a little bit more. But okay, so maybe something like this. So let's think about what a single bond would look like compared to a triple bond. So we said a triple bond is the shortest. Single bond is the longest. So let's first think about what that would look like on here. So here's the triple bond. Bond length is somewhere about here. I just went from the valley all the way up. So here's length of C triple bond O. A single bond is a lot longer. So you only have one bond holding the atoms together instead of 3. Right, so we think about it like, here's triple bond. You have 3 holding it together, pulling them together. Single bond is a lot further apart. So if the student says it's going to be over further, that would mean the length would be longer for the single bond. That's what we just said here. There's the length of the single bond. So far that's good. But then he said it's going to be less deep. All right, so here's the energy for a triple bond. Again, I know it's negative, but just imagine that it was positive. That's the energy required to break it. So it's about 1,000 kilojoules to break it versus 300. So it takes a lot more energy to break this one than to break this one, because you're breaking 3 versus 1. So it looks like what the student said is right. So we'll say yes, I agree. In the CO bond, less electrons are shared. So in the single bond, we have less electrons shared, which is weaker attraction. The single bond only has 2 electrons holding the 2 atoms together versus 6 electrons. All right, weaker attraction results in, so we'll say this results in longer bond length. So single bond is longer. lower bond energy. Which is what that graph showed. We were looking at a single bond versus a triple bond. And as we get into Lewis structures tomorrow, we'll continue to talk about how close they are, how far they are apart. So any other questions on the potential energy curves? Yeah.
The more negative the number is for the potential energy, the more stable it is.
Yes.
Okay, so when it's more stable, you're going to need a lot more energy to break it.
Yes.
Okay.
Yep. So that's why like triple bonds are technically going to be the most stable because it takes the most energy to break it. So since this is like, negative 1100 roughly, that's how much energy is released when the bond is formed. So just the opposite number. So 1100 is how much is required to break it. So triple bond takes the most energy to break because it's the most stable. Single bond will take the least energy to break because it's only 2 electrons versus 6. So it's still, like, both of these are still stable because they're below 0, but triple bond will be more stable than single bond.